Hello everyone, and welcome to today's video on linear transformations of matrices. Personally, I find this topic quite a straightforward one, as long as you're comfortable working with matrices, because it's just about their geometrical meaning. There are quite a few standard matrices to remember from this topic though, and they don't give you much help in the formula booklet. So as long as you can get those right, you're pretty much sorted with this topic. So I've got some top tips here. The first one is to remember the difference between invariant lines and invariant points, because if it's an invariant line, the points could still be moving about on the line, so they're not the same. And the second one is to stay comfortable with all the chapter 6 skills on finding determinants and inverses, because they might throw in algebra into a linear transformation and you then can't rely on your calculator to do that. And the third one is that a transformation matrix is essentially representing where the identity matrix goes to, and that's because multiplying a transformation matrix by the position vector gives the new position vector. But if you multiply anything by the identity matrix, it won't change it. So the new position vector is the same as the transformation matrix if you represent the points using the identity matrix, which is of course 1, 0, 0, 1. So this represents where 1, 0 and 0, 1 are transformed to. And for successive transformations, remember that the matrix for the second transformation goes first. So if we have transformation U followed by transformation V, we need to multiply VU for the matrix, because matrix multiplication isn't commutative. And finally, just being careful with the 3D rotation matrices. One thing that always tripped me up is that the pattern is different for a y-axis rotation, and that's important to remember. There might be an example later on in the video. So the first question, we've been asked to state the matrices and invariant points and lines for the following 3 transformations. So this is sort of testing the difference between the invariant points and lines. So for a reflection in the x-axis, 1, 0 is going to stay the same because it's on the x-axis, and 0, 1 is going to go to 0, minus 1 because of the reflection. So that's the matrix for that reflection. As for the invariant points and lines, invariant points, anything on the x-axis will be an invariant point, because it's a reflection in the x-axis. Anything on the x-axis will stay the same. But additionally, any line which is perpendicular to the x-axis is an invariant line. So I'll do that in a different colour. Invariant line. And we can say anything in the form x equals k. So any vertical line, when reflected in the x-axis, will be invariant, but the points on the line won't be. The next one, stretch of scale factor A parallel to the y-axis. So for this one, 1, 0 will stay the same because it's on the x-axis, and 0, 1, well, it's been stretched parallel to the y-axis by scale factor A. So instead of 1, here we'll have A. So for this one, the only invariant point will be the origin. Every other point, well, there are invariant lines, but the points on the lines are moving around. So the only invariant point is 0, 0. And the invariant lines in this case are the x and y axes. And in addition to that, any line which is parallel to the y-axis, or of the form x equals k, is also going to be an invariant line. So that's not going to change. Next one, we have a rotation of theta degrees anti-clockwise about the z-axis. So for this one, it's going to be a 3 by 3 matrix because it's a 3D transformation. And since it's a rotation about the z-axis, is how I like to remember it, all the z position vectors are going to stay the same. So we can start filling those in. And the other 2 by 2 which goes in the top left hand corner is just our 2 by 2 rotation matrix. So we have cos theta minus sine theta, cos theta. Actually, the derivation of the rotation matrix is quite interesting. And invariant points is going to be anywhere on the z-axis, because it's a rotation about the z-axis. So if the x and y coordinates are already 0, then there's not going to be any change of those. And as we can see from the transformation matrix itself, there's no change for the z-axis. And invariant lines are, we have any line in the xy plane is going to be invariant if it's parallel to the z-axis. Moving on to the next question, which is in fact question 2, not question 3. First of all, we've been given a matrix, and we've been given a question to prove by induction a statement about that matrix. So I will go through this, but there'll be more practice on that in the next video on proof by induction. And then we've been told some details about what that matrix represents from an actual linear transformation perspective. So for the proof by induction, we've been given M is 3a0 1, and step 1 is going to be proving the base case. So we need to show true when n equals 1. That's always the first step when we're proving anything by induction. So m to the 1 is going to be 1 times 3a01, which is 3a01. I mean, this is the easy bit. So true for n equals 1. For the next step, you have to assume that the statement is true for some arbitrary value n equals k. And you actually get a mark just for saying assume true is n equals k, even though all you have to do is substitute n's for k's. So m to the k is 3 to the k a over 2 times 3 to the k minus 1, 0, 1. And then probably the hardest bit is showing it's true for n equals k plus 1. Show true for n equals k plus 1. And for this one, we have 3a01 times 3a01 to the k. That's how we can write that. But we've already assumed that it's true for that matrix to the k. So we can substitute that second one for the expression which they've given us. So 3 to the k, a over 2, 3 to the k minus 1, 0, 1. And we just then need to rearrange that so that instead of k's, we have k's plus 1, k plus 1s. So in order to do that, cross multiplying, we get the 3 to the k plus 1 straight away. And for the second element, we have 3a over 2 times 3 to the k minus 1, add a. So it's just multiplying together the 2 by 2 matrices here. And these will still be 0 and 1. And for the expression here, 3a over 2 times 3 to the k plus 1, add a, that's the same as a over 2 times 3 to the k plus 1, Oh, my bad. This was supposed to be a minus, not a plus. There. Minus 1. Times 3 to the k plus 1 minus, then we'll have a over 2. And then we can simply factorise that. So that's going to give us a over 2 times 3 to the k plus 1 minus 1, which is what we wanted to show. And if we substitute that back into the matrix, I won't actually do it for the sake of time, but that means that we've proven it for n equals k plus 1. And that means that if it's true for any value, it'll be true for the next one. And we started off by showing it was true for n equals 1, therefore it's true for all the natural numbers. That's how proof by induction works. I'm just going to get rid of this quickly, and then we'll move on to the linear transformations part of the question. And remember, there will be more on this stuff in my next video on proof by induction. So, triangle T has vertices A, B, and C, and it's transformed to the triangle T prime by the transformation represented by m to the n. Given that triangle T has an area of 5 centimeters squared and T prime has an area of 1215, we need to determine the value of n and a. And they've also given us where one of the vertices is transformed to. So one of the things we have to know about linear transformation matrices is the determinant of the matrix represents the area scale factor. So in this case, 1215 over 5 is the determinant of the matrix m to the n. This is 243. And then we need to deal with the second bit and actually find the determinant. So the determinant is going to be 2 times 3 to the n, because we had 2 times 3 to the n minus a to the 3. And sorry, the determinant is 3 to the n times 1. So 3 to the n minus 0 times whatever it is there, but it's just going to be 0. So 3 to the n is 243. And you can use logs or a bit of experimentation, gives n equals 5. And then we just need to do the second part, finding the value of a. So the vertex 2 minus 2 is transformed to 123 minus 2. So transformation matrix always goes before the point. We have 3 to the n times a over 2, 3 to the n minus 1, 0, 1, times 2 minus 2. Equals 123 minus 2. And then we need to solve that by actually multiplying together the matrices. So we have 2 times 3 to the n minus a times 3 to the n minus 1 equals 123. We don't need to worry about the lower elements because 0 and 1 means that the minus 2 has just stayed as minus 2. We know n equals 5, so just plugging that in, 2 times 3 to the 5 minus a times 3 to the 5 minus 1 is 123. If you solve that for a, which is pretty straightforward, you get that a equals 3 over 2, which is the correct answer. Moving on to the next question. We've been told that the point P has coordinates 8, 3, 2. And the point Q is the image of P when we reflect that point in the plane y equals 0. So we need to write down the coordinates of Q. So the y coordinate will have changed. And the new point is going to be 8 minus 3, 2. That's the new point. And then we've been told the point R is the image of P under the transformation rotation through 120 degrees anti-clockwise about the y-axis with respect to the right-hand rule. So the right-hand rule bit is not something which they put in exam papers really anymore, or potentially they do, but it's always the right-hand rule. Don't worry about that. It's just normal multiplying matrices and exactly how we usually deal with them. So don't worry about that. Determining the exact coordinates of R then. So we're rotating 120 degrees anti-clockwise about the y-axis and then multiplying by P. So the matrix for rotation about the y-axis of 120 degrees is going to be cos theta, so cos 120, and this will be sine 120, not minus sine 120. That's why the pattern's different for y-axis rotation. And then we just fill the rest of it in with the normal elements. That's separate from that. So that's the rotation matrix. We then need to multiply that by, was it the image of P or Q? The image of P. So 832. And if we actually do that, so we've got minus a half, 0, root 3 over 2, 0, 1, 0, minus root 3 over 2, 0, and minus a half times 8, 3, 2. And that gives us the point R. And if we do that multiplication, we'll get minus a half times 8, so minus 4, and then root 3 over 2 times 2 is root 3. And the y coordinate will stay the same, and the z coordinate becomes minus 4 root 3 minus a half times 2, which is minus 1. So that's the coordinates of the point R. And then for the next one, we've been asked to find the size of the vector P to R. So P to R is going to be, well, we're going from 8 to minus 4 plus root 3, so we're doing minus 12 plus root 3. There's going to be no change in the y direction, and then in the x direction we went from 2 to minus 4 root 3 minus 1, so we have minus 3 minus 4 root 3. So that's the vector P to R, and therefore the size of that vector P to R we can calculate using Pythagoras. So it's the square root of minus 12 plus, what am I doing? Root 3 squared, add minus 3 minus 4 root 3 squared. And if you compute that, you get 2 root 51 is the size of PR. Next part, we've been asked to show that PR to PQ is perpendicular. So this is a new bit from, I suppose, GCSE maths. So if you haven't done the vectors chapter yet, you might not know this, but I'll cover it in a future video. To show that they're perpendicular, we need to do PQ dot PR. And that's going to give 0 if they're perpendicular. So P to R is minus 12 plus root 3, 0, minus 3 minus 4 root 3, and then P to Q is going to be 0, 6, 0. And if you do the dot product, what that means is you multiply these together, and then you add it to the product of these two, and you add it to the product of these two. And clearly for this example, that's going to be 0. And that's how we show that they're perpendicular, which links directly to the next part. Always look to use parts of your answers to previous, parts of the question to avoid doing stuff again. And here we've been asked to determine the exact area of triangle PQR. And since we've just shown that PR and PQ are perpendicular, it's a right angled triangle. So all we need to do is half base times height. And in this case, it's half times the size of PQ times the size of PR. Sorry, not P. Yes, PR. And that's going to give us a so a half times 2 root 51 times the size of PQ, and the size of PQ is just root 6, so it's a half times 2 root 51 times root 6, which is root 51 times 6, or root 306. On to the last question now. So we've been given a matrix which represents the transformation T, and T maps the point x, y, z onto P prime, and P prime has coordinates 3, 7, 4, and we need to find the coordinates of P. And for that, we're going to use inverse matrices. So we're going to use the inverse of this matrix. So I denote that to the -1, and you can use your calculator here because there's no algebra, and multiply that by 374, and that will give x, y, z. And if you do that straight from the calculator, -1/6, -19/6, and 11/6. So that's part A. And then part B, matrix B represents the transformation U, and T followed by U is equivalent to a 90-degree anti-clockwise rotation about the x-axis, and we need to find B. So T followed by U is equivalent to a 90-degree rotation. So that means that U has to come first when we're multiplying the matrices. So it's going to be the matrix B times by the matrix A equals, and then the matrix for a 90-degree anti-clockwise rotation about the x-axis. Well, the x-coordinate is going to remain the same, so we can fill those in. And then our 2x2 matrix in the bottom right-hand corner is just going to be the 2x2 rotation matrix. So cos 90 is 0, minus sine 90 is -1, and then we have 1 and 0 here. And if you do that, so in order to find B, what you're going to do is inverse this matrix on the right hand side. You're going to inverse this one and then multiply it by this one in order to get the matrix B. So B, if you do that, is going to be -4/3, 1/6. It's pretty ugly, but one way they suggested of dealing with this in the answers was actually taking out a factor of 1/6. So I won't do that here, but that would be a easier way of doing it probably. But you can do that. And yeah, that's our final answer for the matrix B. That's it for this video. I hope you found it helpful. If you did, I'd really appreciate it if you could leave a like and share it with your friends. Sorry for the delay with this video. Been pretty busy these last few weeks, but I'm hoping to release a lot more frequently over the Easter holidays, starting with videos for proof by induction and vectors, and then possibly moving on to further mechanics 1. But let me know what videos you'd like to see in the comments. Bye for now.
Chicken jockey!